I thought it might be useful, since we've missed a day of class, to go over the last part of Lecture 6.2. We got through most of it, and then we stopped to do the calcium chloride dissolving activity. And so this is just the last few slides. And there seem to be quite a few misconceptions about evaluating the spontaneity of whether or not something will dissolve, and predicting delta S and delta H. So I think this is probably a really useful review. So I'm just going to start by real quick review that we've talked about the rule of thumb that chemists use, that like dissolves like. Polar substances tend to dissolve in polar solvents, and nonpolar solutes tend to dissolve in nonpolar solvents. And ionic compounds, of course, are extremely polar, so you would expect them to dissolve in water, as most of them do, but not always. So to determine whether or not a process actually occurs, in other words, if it's spontaneous, meaning we don't have to interfere with the process or add anything to it, we, as always, have to look at free energy for the process, delta G. And so I'm going to go over how we do that for dissolving something, for solutions. All right, so just to remind you, the formula for free energy is right here. And we always, always, always have to look at both enthalpy, which is thermal energy, and entropy, which is the dispersion of energy. We have to look at both terms before we can make a prediction whether or not a process will be spontaneous, that is, have a negative free energy value. So I noticed in the homework that a lot of you were making assumptions. You were just, like, let's say, learning about enthalpy and then making assumptions that you could somehow predict entropy from enthalpy. No, all three of these are separate, okay? You need to look at enthalpy separately, the thermal energy. You need to look at entropy completely separately, and then you need to combine those two factors to determine free energy. So I apologize in advance, but I do have 3 dogs and I'm home. So when I say favorable, I mean that the sign of enthalpy and entropy are favorable for a spontaneous process. So we know that delta H, or enthalpy, is favorable when it's negative. That means exothermic. And we know that entropy is favorable when it's increasing, or it has a positive sign. And so when both enthalpy and entropy are favorable, the process will be spontaneous under all conditions. That being spontaneous just means it's going to occur on its own. So if you ever observe something happening, like you observe salt dissolving in water, you know right away that the free energy for dissolving of salt in water is negative. You don't have to do a calculation. All right, so if both entropy and enthalpy are unfavorable, that is, if enthalpy is positive, which is endothermic, right, and entropy is negative, it's decreasing, that process will be non-spontaneous under all temperature conditions. That's not to say you can't make it happen. It just means in order to get it to happen, you need to help it along. You need to provide something for it. All right, the more difficult predictions tend to be when entropy and enthalpy have the same mathematical signs. That is the case when one will be favorable and one will be unfavorable. So in these situations, you can kind of think of enthalpy and entropy as having a tug of war with each other. One is pushing for the process to be spontaneous, and the other is pulling back and saying, nope. And so in those cases, spontaneity depends completely on temperature, okay? And so, for example, if enthalpy is favorable, if it's exothermic, but entropy is unfavorable, if entropy is decreasing, getting more restricted motion, then what term is favorable here? In that case, the enthalpy term is favorable. We would like to we can't really get rid of it, but we'd like to minimize the entropy term. How do we minimize this entropy term? By lowering temperature, okay? So this type of situation will be spontaneous at lower temperatures only. Well, actually totally opposite. If enthalpy is unfavorable, okay, if it's endothermic, that is my dog snorting, not me, and entropy is favorable, okay, it's increasing, it's getting more freedom of motion, then that means that this entropy term is what's going to save us. What's going to make it spontaneous, if anything does. So to emphasize the entropy term when it's already favorable, we want to increase temperature. Okay. All right, make sure you understand that table. Moving on. I thought these diagrams were kind of helpful. Okay, so here's a situation. Again, keep the formula in mind. I still use that formula when I'm predicting spontaneity. So if entropy is increasing, imagine a little teeter-totter here, and enthalpy is decreasing, that means they're both favorable. And if you put the signs in for that, so enthalpy is decreasing, entropy is increasing, that's the situation where free energy will be negative all the time, which is favorable. So the reaction will go on its own. Imagine up at the top of the slide, sliding down. You're going to be able to slide down on your own without any intervention. On the other hand, if entropy is decreasing, which is unfavorable, so if we give that a negative sign, so that this whole entropy term now becomes positive, and enthalpy is increasing, which we also know is unfavorable, that's endothermic, that means that delta G will be positive no matter what we do. So imagine yourself down here, and in order to get to the top, you're going to have to put in some energy. You're going to need outside intervention. It gets more complicated All right, so as I mentioned before, it gets a bit more complicated. As I said, when entropy a little bit more complex, have the same sign. So in this case, entropy have the same side. They both have a negative sign. Sign decreasing. We know that when enthalpy decreases, that is favorable. They have this little star, okay? When entropy decreases, that is unfavorable, and we want to minimize it, okay? So in this case, since we want to minimize entropy, we're going to lower temperature, and at low temperatures, it'll be spontaneous, and we call this an enthalpy-driven process. On the other hand, if enthalpy and entropy are both increasing, that is, they both have a positive sign, we know that endothermic positive sign enthalpy is not favorable, but a positive sign for entropy is. So we want to emphasize, in this case, the entropy term. We do that by raising temperature. And at high temperatures, it becomes a spontaneous process, and we call that entropy-driven. All right, so let's move on to solubility, which is really the whole point of this. We're going to take enthalpy and entropy separately, which is what you always need to do. Okay? You cannot make any predictions about the entropy of a system from the enthalpy of a system. Okay? Some of you are trying to do, many of you are trying to do that. I'm just going to little sidestep for a minute. I think that's because the enthalpy of the system, if it's evolving heat, for example, affects the entropy of the surroundings. But we are not interested in the surroundings here. We're trying to figure out if the system is spontaneous. Anyway, you have to treat enthalpy and entropy separately. Let's look at enthalpy first. There are 3 steps you may remember in the first half of this 6-2 lecture that involve enthalpy. That's heat energy. We need to put in energy to separate solute from solute. So if it's an ionic compound, we're separating ions from each other. Okay, so that takes quite a bit of energy. It's an endothermic process. We also must put in energy to separate solvent from solvent. So in the case of water, that would be hydrogen bonding. Okay, so those cost energy, which is not looking good. However, if the interaction between the solvent and the solute, okay, so that would be in between the individual ions and water molecules. So in other words, if the energy released during solvation is greater than the energy expended by breaking up the solute, and solvent forces, it will likely dissolve. We don't know that for sure because that's just enthalpy. We haven't looked at entropy yet, but that's looking good for spontaneous dissolution. All right, so the attraction between two ions in an ionic compound is called lattice energy. Okay, and so we're going to talk about that for a couple slides, but just so you know what I'm talking about. What does lattice energy depend on? What does lattice energy, which is the strength of the attraction, depend on? We use Coulomb's law. Not sure if you've seen that in physics or maybe last semester, but the strength of lattice energy depends on the charge of the two ions. And so the higher the charge, the stronger the attraction. That makes sense, right? So magnesium oxide would have a higher lattice energy than sodium fluoride because of the cation and anion have a charge of 2. It's also dependent, but to a lesser degree, on the distance between the ions, which is basically a function of the size of the ions, okay? So very small ions can get closer together, which would increase the attraction. Very large ions can't get as close, so they are not as attracted to each other. All right, so what does that say, or how does that impact solubility of an ionic compound? So the lattice energy for sodium fluoride is 910 kilojoules per mole, while that of magnesium oxide is that's almost 4 times more, okay, which makes sense because you're talking about +2 and -2 charges. So since the lattice energy of magnesium oxide is so much higher, it's going to take a lot more energy put in to separate those ions from each other. So in order for magnesium to dissolve, the attraction between the individual ions, that's the magnesium ion and the oxide ion, with water better be really, really strong, or it's not going to want to dissolve. So just kind of to conclude what I just said, in general, if an ionic compound, if the cation and anion only have a +1 or -1 charge, there is a low lattice energy, low energy of attraction, and it's more likely to be soluble in water because it takes less energy to separate the ions. That doesn't mean it will always be soluble because we have to look at other factors, but that's good. And if you are familiar with the solubility table, you will notice in it that all group 1 metals, so that'd be like lithium, sodium, potassium, anytime these group 1 metals are part of an ionic compound, they're soluble. On the other hand, ionic compounds that have individual ions with higher charges and therefore have higher lattice energies tend to be insoluble. Again, not always, but for example, aluminum is +3, calcium is +2. These tend to, if you look at solubility tables, be insoluble. But there are a lot of exceptions, so you cannot make that type of sweeping assumption. Alrighty, you do not have to memorize the solubility table. You are lucky because regular 1212 does have to. I just want you to kind of see the trends we were talking about. Look at all the substances with a + or -1 charge, and they all tend to be soluble. On the other hand, the substances with greater than 1 charge tend to be insoluble. So that now you know how to explain that, hopefully. We're going to shift to talking about entropy now. And because remember, the ultimate predictor of spontaneity, whether or not something's going to happen, is free energy. And that needs to be negative, okay? So it's not enough to just look at enthalpy. There are multiple considerations in looking at entropy when dissolving an ionic compound also. It gets rather complex. I just want to reassure you at this point that we are not going to ask you to make a complex argument. We want to present the complexity, and then at the end, I'll ask you a more basic type of understanding or explanation that we want you to be able to give. All right, so talking about entropy, which is the best way to conceptualize that, is how many modes of motion or what degree of freedom of motion a substance has. The more freedom it has, the more modes of motion it has, the higher the entropy. So in general, when you're talking about an ionic compound dissolving, the entropy of that dissolving process is almost always positive, okay? So, for example, you look at ionic compounds in the solid form, very restricted motion. When they dissolve, much more freedom of motion, so delta S is almost always greater than 0. However, that, of course, is not the whole story. We also must consider the entropy change of the solvent. Okay, we've only looked at it from the perspective of the solute, the ionic compound. What happens when we dissolve ions into water? Does the entropy of the water increase or decrease? Well, you may have guessed. Water molecules, since they surround the ions, all right, so remember how we drew salvation? And the water molecules essentially make a cage around the ions. Well, because of that, the modes of motion, the freedom of motion, the water molecule decreases. And so the entropy change for the solvent tends to be negative, unfavorable. And so the net entropy change depends on the comparative change in entropy of the solute versus the solvent. Are we going to make you pick that apart and analyze it? No, but we do want you to know that it's variable. And quite importantly at this point is higher charged, smaller ions, okay? So like magnesium with +2 charge, calcium with a +2 charge, are going to be solvated more strongly. They're going to have more layers of water molecules surrounding them than a smaller charge like sodium, for example. Okay, so because of that, the overall entropy change of these higher charged ions tends to be unfavorable, or can be. So if you're talking about dissolving something like sodium chloride, you can almost always assume that the entropy change will be favorable, okay, for both overall for the solute and the solvent. However, if you start talking about higher charged ions, for example, calcium chloride, it is likely or a distinct possibility that the entropy change, delta S, will be unfavorable, okay? So that means less than 0 overall. And that could mess with the overall solubility of an ionic compound. So let's kind of wrap this up and let me let you know what level of complexity we want you to grasp. So as I said, overall, this is a very complex balance between the various enthalpy changes of the solute and the solvent and the entropy changes of the solute and solvent. More simply put, if the enthalpy change of the solute and solvent are favorable. So if together they're exothermic, and the entropy change of the solute and solvent, both of them, are also favorable, which would be a positive, you've got a process that will be spontaneous. Delta G is negative. Now, there are all sorts of manipulations of those signs, as we've gone over before, but I just want you to realize the number of things that have to be considered. So let's work out a couple of examples on the level of complexity that you might be expected to explain. So here's a table that gives you thermodynamic data of solution for a bunch of substances. And a question might be, well, actually any of these 4 questions at the top. So let's just take them one at a time. What if we asked you which of the following substances will dissolve in water at room temperature, 25 degrees Celsius, under all conditions, at all temperatures? So you would have to know that would mean that enthalpy is negative for the process and entropy is positive. And so which of these substances is that true for? Well, it's true for lithium chloride, it is true for lithium bromide, and for sodium bromide, and for potassium hydroxide. All of those have a negative enthalpy and a positive entropy, so they would be very soluble in water at room temperature. Well, actually at all temperatures they would be soluble. So that might be a typical question you would be expected to answer and explain. Let's look at one of the other questions. What if I said, all right, so which of these in this table would be insoluble regardless of the temperature? And so then you would have to know, okay, that means that both enthalpy and entropy would be unfavorable. And so are there any samples in that table where enthalpy is positive and entropy is negative? The only one that kind of approaches that is calcium phosphate. I had to really dig. And even that's very slightly soluble under certain conditions, but really not. It's kind of like dropping a piece of chalk in water. You're not going to see much dissolve. But you can see that enthalpy is neutral, okay, but entropy is clearly unfavorable, and so you're really not going to get any significant amount of that to dissolve in water. Okay, third question. These are the tricky ones. When enthalpy is favorable, it's negative, okay, so we want to look for a negative sign, but entropy is unfavorable. Okay, so if they both have negative signs, are there any like that? Calcium chloride. So that means that calcium chloride will be soluble, but really only a certain temperature range. And so what temperature will that be soluble? Look at the favorable factor. What's the favorable factor here? It is enthalpy, right? So we want to minimize the entropy term. Do you remember how to do that? You lower temperature, okay? So calcium chloride will actually increase its solubility as we lower temperature up to a certain point, and then other factors take over. And finally, let's look at the situation when enthalpy is unfavorable, positive, endothermic, and entropy is favorable. So we're looking for a plus sign in both of them. And I forgot to get rid of this. Okay, calcium phosphate is not an example of this scenario. So there are actually several that meet this criterion. Sodium chloride and potassium chloride and potassium bromide. And all of those are soluble. I mean, you know table salt is soluble. But in this case, surprisingly enough, the enthalpy of these solutions is not favorable, which means it just costs net energy to separate the ions from each other and the water from each other versus hydration. But the entropy is favorable. So we want to emphasize the entropy term. How do we do that? We increase temperature, okay? And so what that means is these substances are more soluble at higher temperatures, okay? Which kind of feels intuitively right, doesn't it? So that's it, but I know this is a tricky concept, so there are a couple more slides I'm going to fly through more quickly. The fourth question, and this is a solubility graph, and you should be able to interpret them. Okay, so notice that solubility is on the y-axis, but notice the units are kind of weird. There are always grams of solu in 100 grams of water, okay? So pay attention to that, because sometimes the questions can get tricky, like what's the solubility in 200 grams of water? So just pay attention. And along the x-axis is the temperature. So liquids and solids increase, as you would expect, in general, increase their solubility as temperature increases. Now, there are some exceptions, so if you saw a more comprehensive solubility graph, you would see, but in general. But what's the deal with NH3, ammonia here? It is decreasing its solubility with temperature. That makes sense. So it turns out NH3, if you didn't know, is a gas, and some gases are soluble, but they're always less soluble at higher temperatures. And the big reason for that, the primary reason for that, is the entropy of solution for gases is always unfavorable. So whereas dissolving ionic compounds, sometimes entropy is favorable, sometimes it's unfavorable, for gases, it's always unfavorable. Delta S of solution for a gas is always negative. Because of that, when we increase temperature, what does temperature do? It emphasizes the T delta S term if we increase it. And if we know entropy is unfavorable, increase in temperature is not going to move the free energy term towards a positive or a non-spontaneous process, okay? So we always want low temperatures for gases. But as always, to decide if something's soluble, including gases, we have to consider both enthalpy and entropy. So let's work an example out. And what I would like you to do, and you're going to need to do that in general throughout the rest of this semester, so it's good practice. What are the intermolecular forces that are present in gases? We haven't learned much about gases, but imagine you're down on a molecular level and you're looking at the gas molecules that make up air. Okay, they're really far apart from each other compared to liquids and solids, and we can make the pretty valid assumption that the intermolecular forces between gases are zero. Okay, so we can make the assumption there are no intermolecular forces between gases. So, in other words, the energy taken to separate gas molecules is about zero. All right? So that's favorable for dissolving. Okay? So to look at what the enthalpy might be for dissolving, let's say, oxygen in water, go ahead and draw the Lewis structure for oxygen, molecular oxygen, and for water, and let's look at the interactions that occur between both of them. We know, if you remember your common sense and don't get lost in the actual science like I do sometimes, oxygen dissolves in water, right? We know there's oxygen dissolved in our waterways because that's what the fish live on. But you might ask yourself, if you draw the Lewis structure for oxygen, is totally symmetric. Well, it's nonpolar anyway because oxygen-oxygen bond is nonpolar. It's completely nonpolar, so what is it doing dissolving in a polar solvent like water? Well, in the beginning when we said like dissolves like, we said usually, but that's not always the case. This is a case where unlike dissolves like, or unlike dissolves unlike. All right, so we already know, I already told you that the entropy is always unfavorable for a gas dissolving in water. So if the gas does in fact dissolve like oxygen, what does that say about enthalpy? It says enthalpy has to be favorable, has to be a negative sign. If we know entropy is unfavorable and it happens, enthalpy must be favorable. How is that possible? So again, with gas molecules, there are no intermolecular forces. Okay, so we're going to even assume they don't have London dispersion forces, even though in reality they do, because they're so far apart. Okay. Water, we know, has the hydrogen bonding, dipole-dipole, and London dispersion force, okay, on its own. When oxygen dissolves in water, we now have the interaction of a permanent dipole that water has, dipole-dipole, creating or interacting with the temporary dipole in gas. If you remember discussions about London dispersion forces, they are temporary dipoles, and which means that if something with a permanent dipole or partial charge development approaches a nonpolar substance, it can induce temporary dipoles. And that's going to be a function, how strong that attraction is, or the temporary dipoles, is a function of how easily the electron cloud around that substance can be distorted. And we'll talk about the distorting the electron cloud a bit more in the next slide. All right, so here's kind of a check on your knowledge. So I would suggest pausing the video and reading the question and seeing what you think the answer is. If you guessed B was the answer, you are correct. As temperature increases, the unfavorable entropy term, remember we said entropy is negative always for gases. If temperature increases, this term becomes even more important, which leads to a positive value for free energy. All right, almost there. Let's see if you can kind of apply the knowledge you know about London dispersion forces and solubility and see what you would guess the answer to this question would be. So pause the video, see if you can answer it on your own. So if you didn't get it right, that's perfectly fine. That just means you're a little bit rusty on London dispersion forces. So the magic word is polarizable. So the more polarizable electrons are, the stronger the London dispersion forces will be. And what do we mean by polarizable? Polarizable means the electrons can be distorted more easily. So a larger compound or atom, and krypton is the largest of these, will have more polarizable electrons and therefore have stronger London dispersion forces. And the reason they're more polarizable or more distortable is because these valence electrons are farther away from the nucleus. They're more loosely held. Okay, krypton is so large that by the time you make it to the valence electrons, they're so far away from the nucleus, they really don't feel that nuclear charge very strongly. 2 more slides, yay. So, real quickly, other than the polarizability and temperature, can you think of another factor that will affect the solubility of a gas? It is pressure, right? So pressure from our atmosphere. So you can think, well, that's closed. That's not going to feel any pressure. But in an open container, our atmosphere is always exerting a downward pressure on the surface, and that doesn't have much of an effect on liquids and solids, but it has a very pronounced effect on gases. And so the higher the pressure, whether it's from our atmosphere or artificially induced pressure, the more solubility a gas will be. So you can think about it as if you increase the pressure, the external pressure, you're kind of pushing these gas molecules down into the solution, and they will be more soluble. So you can see a graph here, the function of solubility of a gas with pressure. And as we said, as pressure increases, solubility also increases. That is it. And so I will be there Thursday for your test, and I should be in my office tomorrow too. Talk to you later.